Folks, this is the first lecture of week 4, and I have some items on the agenda today. First, some miscellaneous comments, and these are going to help you to answer some of the questions that you have already seen, but perhaps a review would not hurt. And then I will do our final problem from uh, doing finite element calculations with shell elements. Okay. For a while, for maybe a week or so after I do this lecture, we put the shell elements aside, and then we come back to it in the last week of the uh, first half of the course. All right. So first of all, let me quickly remind you about the concept of parallel and springs in series. So if you look at a situation like this, these rods, if these are two rods, for example, of different materials, you can pretend or you can approximate that rod with a spring of a stiffness AE over L, where A and E and L are associated with this top rod. Now, of course, the top rod and the bottom rod seem to have the same length. And if that's the case, they have the same L, but they may have different cross section and different Young's moduli, two different materials. So these two actually act in parallel. So when you take the stiffness, the equivalent stiffness of these two, you add up adding stiffness of material 1 to material 2, or bar 1 to bar 2. So it's going to be A1 E1 over L1 for that, and K2 is going to be A2 E2 over L2. Of course, they have the same L's, we know that. And then you add them, you get K1 plus K2. So these two springs acting in parallel can be replaced with a single spring of stiffness K1 plus K2. Now, when you take this spring and the other spring, because the other end of the spring of this bar on the right-hand side, this is moving, this is not fixed. What you did on the left side and this spring from material 3 are in series. So material 3, the bar with material 3 has its own stiffness, which is A1 E1, or sorry, A3 E3 over L3. Whatever it happens to be is going to be in series with that effective stiffness that you replace with the two on the left. So this was the parallel springs. This is the stiffness of this spring of material 3, and the two meaning the replacing this with 1 and leaving this thing as it is are going to act in series, and therefore the effective stiffness of the overall structure of the structure can be calculated from that expression. 1 over K effective, everything, okay? Stiffness of the whole structure is 1 over K1 plus K2, because these are in parallel, and then plus 1 over K3, because this spring on the right side is in series with when you replace these two with a single spring. All right. The other thing is that I've told you many times that if you make a single finite element run and look at the numbers and the colors, you might as well throw it in garbage because it's totally useless. What one needs to do is to perform a mesh convergence study or a sensitivity study. And all that means with respect to mesh, of course. Of course, what that means is that let's pretend that your modeling was okay. In other words, you did not make very dramatic assumptions so that it completely changed the nature of the problem. Let's say your modeling was okay. And you make a finite element model of that thing that you made and run it. You have no idea whether the numbers are actually depending on the size of the elements used. So that's what I mean by mesh conversions. In other words, now you run it again. If you have access to a better quality element, use it. For example, if your initial run was in linear element, the second run, I suggest you do it in parabolic elements, okay? More sophisticated, and compare the results of the two. And when I say compare the results of the two, you have to look at critical places. Don't just look at the top number in your contour legend and compare those, because those may be actually totally artificial coming from the way you model the problem. Okay, so look at the critical spot and compare the two results. If they are too far apart in your judgment, neither one of them is acceptable. Just throw away the linear one, keep the quadratic one or parabolic one, and now start making the mesh smaller and smaller and smaller in critical area. That's the magic word, in critical areas. So, and then compare the results. And if eventually you see that there is really not much change in going from a mesh to a finer mesh in the critical area, then you have some confidence that the results are not depending on the mesh that you use. And that's what we mean by mesh conversion study. Now, in the setup of doing a finite element calculation on the test or on quiz, etc., I'm not asking you to do that, but that's always in the background. If you're being paid to do finite elements down the road, hopefully some of you will, or if you're doing this thing for your project or your research, etc., do not forget that one run, tear it up, throw it in garbage. Okay, you really have to do mesh conversion study, and this is all based on the assumption, that your initial modeling of the problem was okay. Because if your initial modeling is inappropriate, then yes, you can do mesh conversion study on a inappropriate model, and eventually things settle down and you take it. But those numbers are not reliable because your initial model of the whole physical problem was erroneous. Anyway, you should keep that in mind. All right. Now let's go back and talk about the type of elements that we call solids. Now, CATIA does not call it solids; they call it tetrahedral elements or hexahedral elements. But anyway, let me use the standard shape that CATIA uses. Solid elements. These are linear solid elements. Each element has 4 nodes, and each node has 3 degrees of freedom, 3 translations in X, Y, Z direction. When you go to parabolic version of that, there are some additional nodes here. There are intermediate nodes. So therefore, there's altogether, there is 6. You can see that's 6. Let me show. Sorry, hang in there. How many nodes do we have? Oh, we missed some. Whoa, 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 whoa. God, terrible. Got them all? Okay, sorry. So each element will have 10 nodes, and each node will have 3 degrees of freedom. So altogether you have, for this, 30 degrees of freedom. Rotations are not degrees of freedom for a standard solid elements, okay? That's why when you go to user-defined restraint, notice that there is 3 translations, 3 rotations. Whether you check the rotations or not makes absolutely no difference for solid elements, okay? Now, if you want a fancier mesh, and the fancier mesh are what are shown here, like the shoe boxes, okay? You can either have it like that, or like so, These are called hex elements or break elements, or I call them shoe boxes. And each node, once again, has 3 translations as degrees of freedom. So you multiply the number of rows by 3, you get total number of degrees of freedom for this. And the same thing down here. This is 20. If you count the number of nodes, it's going to be 20. And 20 times 3 is going to be 60, essentially, unknowns associated with the problem. Let's make sure that this actually is 20. I'm pretty sure it is, because, so let's see, now on this side you have 3 and 3 is 6 and 2 is 8. Yeah, 8 and 8 is 16, plus these 4 is 20 nodes. Okay, these kind of elements, you cannot do it in this generative structure analysis within CATIA. In order to get a fancy mesh like that, these hex elements, you have to go to the advanced meshing tool. A collapsed version, if you take this one on the left and you collapse these 3 nodes, if you collapse these nodes 1, 2, 3, what you get is a wedge element. So essentially, a wedge element is a modified version of the one on the left, and of course you get something that looks like a wedge. Okay, let's move on. Shell elements. The standard ones that you have in the generative structure analysis is either linear, these go on surfaces, either linear or parabolic. Okay. Now, if you want these kind of elements, okay, the 4-sided one, which are incidentally called quad, okay, you have to go to the advanced meshing tool in order to get that. Okay, you cannot get elements like that in the generative structure analysis, which is the main FEA module of the CATIA program. Incidentally, CATIA call these things a octree triangle. I call them shell element, 3-noded or shell or 4-noded shell elements. Either way, you should be familiar with all the terminologies. Okay. All right. Remember, shell elements go on surfaces essentially, and solid element go into, in principle, kind of bulky objects, things that are not shell-like. You can, if you have sufficient computing power, you can solve everything with solid elements that we discussed in the previous slide. But life is not that simple. Now, if your structure is essentially one-dimensional, we use beam elements, okay? For example, for I don't know, maybe your let's hypothetically say diving board. Yeah, you might say, well, can I not solve that thing with shell element? The answer is yes, you can. But you can get, if you're interested in getting deflections and things like that, and frequencies, natural frequencies, then beam element will do with the cross section is that square that you see in the diving board. Or, for example, your I-beams that are supporting roofs and columns and things like that are, generally speaking, modeled with beam elements. Now, when it comes to any one of these elements, let's go, for example, let's go to the top one. If any one of these angles is very small, then you get kind of obscured shape, which is, yes, it is like a pyramid, but with a very distorted or angles which are not acceptable. If these angles are very small or very close to the 180 degrees, either these or shells, or, well, here we don't have, of course, that situation, but if you have any of these angles very close to 0 or very close to 180 degrees, we say that they're distorted. Okay? So that's really what it does. You should try to avoid, there should be an element, you should be able to avoid such scenarios. Otherwise, you're going to get a warning message, or, well, even if you don't get a warning message, the results are going to be fairly unreliable if there are too many of them available. Okay, so this was the situation. I'm talking about linear elements now, two solid element. Linear looks like that. Tetrahedral, what Katia calls tetrahedral looks like that. And then each node has 3 degrees of freedom, 3 translation. When you go shell elements, linear shell elements, go on surfaces, each node has 6 degrees of freedom, 3 translation and 3 rotations. And beam elements are essentially one-dimensional structure, and each node, so linear beam element has 2 nodes, and each node has uh, 6 degrees of freedom. So there's something missing here. This angle is missing. Yeah, there's an angle here. This is angle about Z. Something missing. Okay, very good. All right, so that takes care of a review of what we had to do for the past 3 weeks. Now, I want to do my last shell problem for now. So we're going to take a cylindrical pressure vessel. We're assuming this is a thin-walled pressure vessel, because if it's a thick wall, then you either have to model it with solid elements, or you have to be more careful about uh, interpreting the results. So a thick walled cylinder, such as, for example, uh, the the uh, such as the firing tube of a tank or a barrel. The barrel. Okay, the barrel of a gun, for example, that has to be done with solid elements to get good result. But if you're dealing with thin wall pressure vessels, such as, I don't know, maybe uh, propane tank and stuff like that, even pop can has liquid in it. Of course, if you're pressurizing it, then a thin wall pressure vessel will do okay. Now, uh, on purpose, what I'm going to do is analyze this problem by taking a sector of the structure that is not 90 degrees. Okay. Now, what do I mean by that? First of all, the details are given here. Now, we have analytical formulas from our second year deformable bodies. So there's a hoop stress, there's an axial stress, and the radial stress. Radial stress is very close to zero. So in fact, when you use shell elements, the assumption in shell element, no, the assumption in shell element is that the stress through the thickness is zero. Okay. And this is a thin wall structure. That's a very good approximation. Okay. But the hoop stress and the axial stress were derived for you in your second year class. Now, when you look at this problem, first of all, you can take a cut in the middle. What's on the top and what's on the bottom, they look exactly the same and they will behave exactly the same. It's not just a matter of looking. Don't look at the geometry says, oh, I can cut this thing in the middle because there's one plane of symmetry because the top and the bottom are the same. That is not good enough for finite element purposes. The loads and constraints, the load and restraints must also be so that there is finite element symmetry. Now, in this particular case, because of the nature of the loading and things like that, now it's obvious that the top and the bottom are symmetric. And in fact, if you take any sector of this cylinder, for example, a 90-degree sector, a 30-degree sector, a 40-degree sector, right next to each other, they all behave the same way. Now, the reason I take let's hypothetically say a 30-degree sector, is because one of the edges, which is going to be one of these, is going to lie in, for example, one of the standard planes, such as XZ or YZ, etc. But the other one, because you took a 30-degree sector, okay, so that's what I'm going to do. 45-degree sector. The dimensions are given here. Let's go ahead and make it. Oh, by the way, when it comes to making this, so several options you've got. The easiest one is you draw this L this shape, okay, draw this L, and just revolve it in order to get that 30-degree sector. That's one option. And if the advantage of doing it like that is that when you take this inverted L or this L, inverted L, and revolve it to get the surface, the top and the side are actually, in principle, it's a single surface, and therefore when you mesh it, it'll do both of them at the same time. If you put the two-dimensional property on it to specify its thickness, you'll do it at the same time. But if you, for example, just hypothetically, if you did an arc and revolve it to get this top surface, and a vertical line and revolve it to get the side surface, these two side surfaces will not talk to each other. So when you mesh them, you have to do them separately, and then you have to put properties on it separately. And even then, they may look okay, but these nodes on the top and the side do not talk to each other. When you pressurize, this whole thing will fall apart, will just move away as a rigid body or something like that. Even if you created a solid object, an extracted solid object means something like that, which looks the grayish in the part design, then you extracted the top surface and the side surface, you will have to join them, because otherwise these surfaces do not talk to each other. If you're following the book, I think that's how I'm doing it. In other words, you created a 30-degree sector solid and then extract the top and the side and then join them together. That's crazy. In fact, in the book, I may be doing connections, which I'm not, haven't talked about it in the class. Anyway, that's what I'm going to do. I'm going to draw this inverted L and rotate it by by 30 degrees. Now, in the class, if there is time, those of you who are watching the video, in the class, if I have time, I may go and do it these other ways to show people that it's going to fall apart. But I'm not going to do that here. All right, let's go ahead. Just dimensions. The height of this thing is 40. All right, good. So let's go ahead here. Start with the part file. Notice that I'm no longer making all this fuss about saving things and stuff that you have to do it in an organized way. But after you wrote the quiz, you know that if you don't do it, there's going to be a problem. All right, so there we are. I'm using the wireframe and surface design in order to draw that. So let me draw my L. This is a 30-degree sector and half the height are already done with a cut. So this is going to be okay. This is going to be 20 inches. Our units are in millimeters. Not a good idea. Let me go ahead and change this thing. So we have tools options. Change the units to millimeters. Sorry, change the unit to inches. Okay, and pressure, I'm going to change it to PSI. So tools options, I forgot to do that. Okay, so let's find the pressure. Click on the magnitude to sort it out, and then find the pressure. You see. Sure. Right there, I'm going to change that thing to PSI. All right, good. Okay, so I'm going to make this thing 20, half the height. Okay. And this is going to be 5. That is the radius of the shell or the tank. There we are. I'm going to exit and revolve it. Axis is about the z-axis. And I'll go 30 degrees on purpose. Now notice that because of what I've done, this L was in the YZ plane. The sketch that I had was in the YZ plane. This sketch was in the YZ plane. Okay? No problem as far as applying restraints is concerned later on. But the other two edges are in none of these vertical plane, not YZ, not XZ, obviously not XY. Okay, so that's why I'm going to create a local coordinate system here and use it. Okay, right now when I'm at it, I'm going to do that. So here is an axis system. See that axis system? You can put it in different places. You can put it in this corner. You can put it in that corner. It really doesn't matter. Just so that you can see it better, I'm going to put the origin at this corner. See this? Origin at this corner. All right. And you can rotate this thing by 30 degrees, or the alternative is to say, okay, I want, for example, this Y, see this Y, to be aligned with that edge. That'll do the same thing, because just to convince you, so I'm going to select the Y, this is the Y axis, to be aligned with this edge. And notice that it did switch it so that Y is along that. And now, of course, because of the way things are, this X is perpendicular to that edge. Actually, it may not be. Let me see for a second. Oh, it is because of, yeah, it is. You can see that. If not, you rotate it until it becomes, but I'm pretty sure it's going to be okay. Instead of, in the class, when we did the axis system, we rotated them. There, the situation was a little bit different. But here, because of selected the direction of the y-axis, it did it for me. What I wanted. All right, good. So let's apply material to this thing. Apply material. I think we made it out of steel. Just remember that these stresses, PR over T and PR over 2T, do not depend whether it's aluminum or steel. The stresses don't matter, but the strains do. Okay, but okay. So we're going to make it out of steel on that part. Good. And I don't have to join it because of the way I did it, inverted L and revolved it, it is automatically going to be a single surface when I try to mesh it, or when I try to put the thickness on it. Now, if you want, you can join it, but it's not going to do you any harm or any good. All right, so let's go ahead to the analysis and simulation, generative structure analysis. We are doing a static analysis, right? Say okay. Very good. Notice that the bottom of the tree static case has been put. Now let's do the meshing. Here is the octree triangle mesher or shell elements, 3-noded shell element. And what am I referring to? I'm referring to these fellows. Okay. So I'm going to click on that, and I'm going to click on this. Okay. Notice that it meshes the whole thing. Now, in the events that you want a finer mesh here, you can do that. See that? There's a local tab here. You select it. You say edge distribution, and you select add. And it says, where do you want a finer mesh? Maybe around there. Yeah, how about 20? That's fine. That's fine. And then we say okay. And if you want to see the mesh, right-click mesh visualization. There we go. You can see that it put a finer mesh around that based on the distribution that I gave it 20, and everything else, it just took the gigantic element. This is too big. This is too big, So be aware of the fact that without mesh conversion study, garbage in, garbage out. But anyway, so what I'm going to do actually, let me double check on this thing. Make sure it's parabolic. And, I'm going to make this thing a little bit smaller. Maybe try it one. More respectable. Activate. So it's a finer mesh, okay, but over here I still have my 20. All right, if these things are bothering you, just deactivate it. And if you don't want to see that fellow, if you don't want to see this fellow or the edge distribution, just hide it. There we are. Okay, good. Oh, wait a minute. Yeah, excellent. Now we apply 2D property on it. Click on it. Because the whole thing, the way it was done, no join was required. The whole thing is meshed. I think the thickness of that problem was 0.1 inch. Yeah, that's good. And of course, the properties selected. Good. don't forget, if you want this thing to be marked on a quiz on a final exam, you have to give me the part and the analysis, both of them. Okay? Please do not create these and then go and rename them by right clicking and changing it to the name that you want, because very often people go and right click that and put their name on it and the student ID number. That is a recipe for disaster. This is not a Word document. This is not a PDF document. These are critical files in the database that's generated automatically by CATIA. So do not do right clicking and renaming. Good, good. So let me hide the sketch, because I don't want to put a sketch a restraint accidentally on this, because it will not see it. Let me hide it. The sketch is gone. Now it's all right. So let's see. Why don't we apply first of all this bottom one? See that? So I click on that. This is in the, first of all, let me call it bottom so that you know what it is. Bottom. And this is in the XY planar symmetry. As soon as you say XY planar symmetry, no Z translation. And rotation's exactly the opposite. Good. Now let's do these two edges. Click. I'll call it, this is the YZ planar symmetry, YZ global YZ symmetry global axis, because those edges were already sitting in the YZ plane. So uncheck all of these first of all. So this edge and that edge in the global, as soon as you say YZ, no displacement in X. And rotation is exactly the opposite. Good. Do another one. Let me uncheck all of these. I write down what I have here. And this is, what is that? Just look at that corner system up here. No, it's not global. It's user. And it's this user. And notice that these two edges, see that? This edge and that edge. Whoops. Oh, this edge and that edge lies in the local YZ. See that? Local YZ. Local YZ. So I'm going to rename this thing to be YZ Symmetry Access System 2. Or 1, actually. I think that's called Access System 1. Access System 1. Yeah, notice it's selected here. Access System 1. Okay, now do that. As soon as say YZ, no displacement in X. And rotations opposite. And then we say okay. Very good. And finally, we're going to apply pressure on this face and that face. Unfortunately, when it comes to pressure, you have to put on both of them. Okay. Okay, there we are. But this direction is wrong. In other words, minus 100 psi, because the other one was creating such vacuum inside of the tube, sucking all the air out. But there we are. Now you can see. Pointing out, pointing out. All right. Don't forget to save. Something that I'm not doing. It's not a good idea. Run it. Okay, let's look at the deformation. This is just going to get like a balloon. It's going to expand. Otherwise, we may have made error. Now, if you say, well, wait a minute, why is this guy not expanding? Because this top face is so flimsy that actually you cannot see the motion of this fellow. If you want to see the motion of this fellow, if you insist on seeing it, let me change the scale. Where is that scale here? Right there. Let me put maybe a 10. Okay, let me zoom in and see whether we can see the motion of this fellow, like expanding like a balloon. If not, we make it even higher. I can still not see it. So let me go ahead and make it even higher. I'll make it 30. Ah, you can see that now. You see? It's moving. Let me go back here, make this thing 100. There. It is expanding. You can see that. See? Now, obviously, when you make it 100, this top is going to go crazy, nuts, right? Very good. So fine. Let's change back the scale to default. There. Now, how about principal stresses? Because after all, we can compare our results with these analytical formulas. So your R was 5, okay, and your T was 0.1. So 5 over 0.1 is 50. So 5,000 in the hoop and 2,500 psi in the axial. So let's go ahead and plot the principal stresses. We know how to do that. Let me get this thing out. These are displacement. These are principal stresses in the form of a symbol. Let's move in. Both are tensile. This must be 2,500. And hallelujah, it is. It says, sorry, this is the hoop. This is the axial. 2,500 theoretically. It says 2,400. And this one is supposed to be 5,000. It's almost almost 5,000, 4,760. Now, let's go back here. In fact, if you go further down here, the results are even going to be closer. Because there, we may have been too close to the top. Let's see now. Just watch these. These are close to the bottom. This should be closer to 2,500. Sorry, this is the hoop. This one, it says 2,360. And this one should be close to 5,000. It's 4,900. Yeah, and if you choose a finer mesh, my mesh is kind of big here, but that's okay. So now, let's check a few things here. If you want this thing displayed, if you look at the von Mises stress, and change the rendering to your shading, you can see that over here, pretty much it's all the same color. You can see that, and the values are given there. So the von Mises stress is the down here. This blue region is there, and the reason on the top you have a big stresses is because there is a seam here. Okay, essentially this is a cantilever beam, etc. So it's not surprising that you have failure here, because based on common sense, that's a critical point for failure, and that's why it's so all this red. This is gigantic stress. 15,000, 100. Is that 150,000 psi? Now remember that yield strength for steel is knock down 3 zeros from 30 million, which is the Young's modulus, and you get 300,000, 300, knock down 3 zeros. So that's going to be 30 times, hang in there, 30, the Young's modulus is 30 million. Knock down 3 zeros, so that's going to be 30,000 psi. 30,000 psi. And this has severely exceeded that. Assuming that we trust these, because we have not done a mesh conversion study, I don't know. What I'm saying is that this is 150,000 psi. Yield strength for steel, structural steel, is 30,000 psi. Now keep in mind that if these are, for example, just hypothetically, containers that carry hydrogen for fuel cell and things like that, they're not made of structural steel that you use for I-beams and buildings and things like that. They are high strength steel, and so that depends on your situation. Now, one thing I want to show you, and this is very useful. You might say, you know what, I want to look at only stresses in this area. Okay, but right now, because those stresses are masking, those top stresses are masking what I can see, they're very large. They're masking the stuff here. So what I'm going to do is I'm going to say, okay, you know what? I'm going to deactivate this, and I'm going to show you something that's very useful, and that is making a group. First of all, these are unnecessary. I'm going to hide them. All these restraints are unnecessary. Hide them. Good, good. So there is a toolbar here which says group. I've never used it, but here's an opportunity for you to see. And there are different ways of making a group. For example, I can make a box group, I can make a surface group, I can make a sphere group. So I want to make a box in this area, or maybe a sphere in this area. I'll do a box, okay? A box in this area. Now notice I made a gigantic box here, and I'm going to resize it. To resize it, you see that? Click on this, you can resize it. So I'm going to move this thing down so that I go away from that top piece. And there's no reason to do this but if you feel like it, sometimes you may have to make it small. Oh, wait a minute. Oops. It's kind of, wait a minute. There we are. I want the area that I want to be enclosed in that box. Okay. And then say, okay. So when I activate this von Mises stress, I say, you know what? I don't want you to show me everything. Just, there's a selection box here. There's a selection tab here. You select it and say, just show me the box. Just right there. There's a box group. Double click on it, sends it down there. And then you say, okay, right click and hide the box. There we are. Hallelujah. So make that the material shading. You might say, what the heck is this? What the heck is this? Why are these like that? Well, look at the numbers. The numbers are almost so close to each other that essentially it becomes kind of a noise. Okay? So this is a good sign of how to concentrate in a certain area that you may be interested. One last thing. Notice that these colors are all mixed up. If you double click on it and you say more, there's an option, there is a box here. See that? There's a box. Sorry, there's a more here. See that? More. Actually, no, less. There is a box here. You just click on this box. See that? A box with 3 dots. It says just showed me don't show me the smooth version. Smooth means all these colors are mixed up. And now you can see that they're distinct colors. They're not merging into each other. Okay, I hope you found this thing useful. So groups are very useful for real calculations. Real calculation meaning that when you're not, when you're asked to find detailed things. Good luck. Oh, by the way, in the class, I noticed that this presentation is about 45 minutes. In the class, I had more time, another 5-10 minutes, and therefore I've done a redo of this where I created certain surfaces that if I did not join, they would be problematic. If you want, talk to your friends and find out what was done in the class.